Okay, welcome everybody to the .NET User Group today. Great to have you joining us from wherever you are around the world, in Adelaide, South Australia, or further afield. My name's David Gardner, and it's great to have you with us today. Excited to have Rob Richardson joining us to talk about databases in the microservices world shortly. But first, a few notices to go through. So we're on Meetup. We're on Twitter, on Facebook, so love to have you follow us on one of those platforms, and do feel free to share about your experiences today and let other people know about what the group is up to. We generally meet on the second Wednesday of each month, and today we continue that tradition. In next year, we're sort of looking for speakers and also for some venues. With all the COVID stuff happening, it's not clear where we'll be able to meet. Hopefully the restrictions are sort of being eased here in Adelaide, so that will make things a bit easier. But do feel free to get in touch. There's one of my email addresses there if you're interested in speaking, either in person or remotely, or if you've got some ideas for a venue that we could use to meet in person next year. Hopefully that's going to be possible. So we have a little What's News segment just to bring everyone up to date with what's happened since the last time we met a month ago. Hasn't been an update to VS Code, so my prediction is that will come out later this afternoon, probably. It always seems to be around this week that there's a new update, so there's only just the current sort of minor update to 151 at the moment. But there was some updates to Visual Studio 2019 that came out overnight. So we've now got 16.8.3 in the GA release, which has got some bug fixes and some security fixes. So that's good to see that coming out. Likewise, there's also a new preview release that came out overnight for 16.9. Some of the improvements there, some more enhancements to get productivity, some more .NET productivity enhancements as well, some new refactorings, things like when you add a reference to a type, it'll now potentially add the using in for you automatically. Some improvements to C++ if you're into that. But also one that I've actually seen already, that they've made some changes to the installer now, that it doesn't need to elevate all the time. So apparently they did some of the users for the preview had that feature already. I managed to get it on one of my machines and not the other. So yeah, you can run the installer. It just runs automatically. You don't get the UAC prompt, but then when you go do the install or the upgrade, then you'll get the UAC. So that's just a bit nicer. And other bug fixes there. .NET Core, no changes to some of the older LTS releases, but there was an update to .NET 5 that went out overnight. And interestingly, there was a blog post about this in the last few days. It's also being pushed out through Windows updates. So you might see as you are installing the Patch Tuesday updates that there's also a .NET 5 update as well. So they've added that as a way to push out those fixes to people. So yeah, something to be aware of. And I guess potentially if you're in an organisation that's got an IT department, they might be interested in knowing that that's going to happen as well. We really appreciate the support we get from Encode Talent, and I don't know if Simon's got his video on or he's just listening. So if he's not able to see the video, then he won't be able to see what I've done to his picture. But I thought I'd make sort of Christmassy it up a bit this month. So you can see what I've done. Yeah, so we do appreciate their support, particularly in this time when we can't meet together, but also when we do meet, they help us out with pizzas and just a great support for our group as well, and promoting what we're doing. So we really appreciate them, and do encourage you to get in touch with them if you're looking for developers, or if you're a developer who's looking for a new place to work. Get in touch with Encode Talent. Just a reminder about the Slack channel that our group is a part of, as are a number of other user groups in Adelaide, the Heaps Good Dev Slack. There's a QR code there that will give you the link to be able to join up to that. There's a few hundred people there, mostly Adelaide-based, not just .NET, but in other user groups as well, so front end and different languages. So yeah, really supportive and knowledgeable group of people. So I encourage you to get involved with that Slack group as well, just to keep those conversations happening during the rest of the month. Thanks everyone for coming, and do let me know if you want to speak or help out in any other way. Now, just a few more things. This meeting, as well as having Rob here today, also was sort of mentioned that this is going to be the Adelaide launch of .NET 5, and by doing that it means we get to give away some prizes. So a quick dot point view of some of the highlights of .NET 5, just if you weren't aware. In C# we've got records, we've got relational pattern matching, top level statements and source generators. In F# they've introduced interpolated strings, and in VB they're supporting additional project types. There's some improvements to system.text.json, single file apps and app trimming, support for Windows ARM64 and using the intrinsic, so making sure that the native instructions are being used for particular things in .NET, and a lot of performance improvements, and also more nullable reference type annotations in the runtime libraries, which is cool. As well as performance improvements in garbage collection, system.text.json, smaller container sizes, and a whole bunch of other improvements. So definitely worth a look at .NET 5. I know that's sort of on my radar, looking at some projects to see if we can upgrade to those. There are some breaking changes, so it's something you'll need to have a close look at to see if it's a simple upgrade or if there's a bit more involved. So there is going to be some .NET swag given away, but I'm not going to give it away now. We've got Rob's talk to enjoy first. So at the end of the talk, so you'll need to stay on for the call, I'm going to give you a URL and a promo code, and the first 20 people that manage to sign in to that will be able to get some swag sent out to them. So that's it.
Okay, let's talk about databases in the microservices world. Here's the part where I say I'm definitely going to post the slides on my site tonight, and they are posted right now. If you go to robrich.org and click on presentations here at the top, here's databases in the microservices world at Adelaide.NET User Group, and you can click right here to get to the slides that we're going to look at today. They are online right now. I've been that guy who's chased the speaker for months trying to get the slides, and it's never worked out very well. So I want to make sure that I post the slides ahead of the talk. While you're here on my site, click on About Me, and you'll get to this page that talks about some of the things that I've done recently. I'm a Microsoft MVP, a friend of Redgate. AZ GiveCamp is really cool. AZ GiveCamp is a volunteer organization that builds software for charities that otherwise couldn't afford software. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. Or if you'd like a GiveCamp here in Adelaide, hit me up on email or on Twitter, and let's see if we can get philanthropy installed in your neighborhood too. Some of the other things that I've done, SQL Source Control Basics. Mine was Chapter 8. That was really cool. I worked on the Gulp team in version 2 and version 3 as a core contributor, so I got to help shape the architecture of Gulp. One of the things I'm particularly proud of is I replied to a .NET Rocks podcast episode. They read my comment on the air, and they sent me a mug. Woohoo! So there's my claim to fame, is my coveted .NET Rocks mug. And if you'd like a .NET Rocks, no, I'm just kidding. They actually don't give away .NET Rocks mugs anymore. They give away other things. So databases in the microservices world. Let's dig in. We talked about this guy. As we look at databases in the microservices world, let's first look at architecture, because that kind of lends us towards how we build databases. As we look at architecture, we kind of build up this type of experience. We started out with spaghetti, we moved to lasagna, and then we moved from there to ravioli. Here's a big ball of mud. Here's an n-tier architecture, each of the layers of the lasagna. And here's microservices, where we have little nuggets of functionality. I really like this analogy. I just think it's a really cool way to describe that problem. And it's fun to see the evolution of our industry from spaghetti to lasagna to n-tier or to ravioli architecture. I don't think we're done, but microservices is a fun place to be. Showing this a little bit differently, here's a monolith here on the left, and here's microservices on the right. With a monolith, we focused on building all of the pieces into one executable, one deployable piece. And we chose that because deployment was hard, and so we didn't want to do it very often. On the upside, all of the pieces of our application would get deployed together, and so, well, our internals were internal. And so we would deploy that piece, and maybe we'd get on the conference call Friday after work, and we'd stay on the conference call like 24, 36 hours. Sometime on Sunday afternoon, it all worked, and then we'd all hang up and go to bed. We moved towards microservices because each piece was so much smaller and simpler. There wasn't this big, call on Friday evening to try and get everything deployed. We got deployment kind of under control. We could deploy a lot easier. And so each of these little pieces accomplished a single task, and we could deploy each one independently. We could scale them independently, and it was really great. As we move into microservices, we get really elegant separation between the code. Each of our microservices does one thing, and they own their own data, which is really cool. One of the downsides of microservices is now, as we have all these microservices, our internals have web addresses. So as we go to secure our microservices, maybe a service mesh comes into play and makes that a little bit easier. But we have lots of little microservices, and each one owns its own data. This microservice might call into this microservice to get at this data, and it may call into this microservice to get at this data. That's totally fine. Each microservice owns its own data. So microservices, it does one small job. It's easy to deploy with containers. We can scale them independently, and they're really easy to replace when we need to upgrade it or when we need to just wholesale replace it with a very different functionality. We can rip out that one microservice and we can replace it with a microservice that does a different job or an upgraded job. And one of the key pieces of microservice, that it owns its own data. And we very specifically do this so that each microservice that owns its own data doesn't need to check in with the organization to see who's using this column. If we're not using this column, then this column is unneeded and we can remove it from our database. Or if we need to add a column, we just add it to our data store. Each microservice owns its own data so that it can control the lifespan and evolution of that data store. Now that's interesting, but usually we do this. So we've really elegantly separated our application into microservices, and then we go grab the database we used last year. And we have one big database. Oops. Well, why do we do this? Why do we, spend so much time refactoring into microservices only just to default to a same monolithic database? Well, as we start looking at the failure analysis here, why did we choose a monolithic database with microservices? The one that jumps out is because the DBA said no. Well, that's interesting. The DBA's job is to maintain the uptime and integrity of the data. And so one way to do that is to block changes as much as possible. We don't want to change things because changing things could potentially lead to risk. The goal is to protect customer data. Well, kind of. If we can move to a different mindset where a DBA's job is not so much to guard against changes, but to facilitate changes safely, then I think we can get around that, the DBA said no. So the DBA said no because, well, they didn't want to do it, but also lots of little data stores can be problematic. If we have lots of little data stores, then maybe we don't back one up, or we don't end up replacing the SA password with something more secure. And so that mechanism of ensuring that each database is backed up continuously and regularly, and also enrolled in the authentication scheme to make sure that its data is secure, those are the two pieces that, for the most part, we need to solve in a really elegant way before we can start to dig into lots of little databases. If we can get security and backup, then we can do a whole lot more experimentation with different types of data stores and hopefully get to that micro database mechanism. So if we must use a monolithic database with our microservices, we can start to carve out little pieces of functionality that will do interesting things. Now, each of these little pieces of functionality we can think of as a bounded context. We'll draw a little circle around this portion of the database, and we'll call that a bounded context for this particular task. Now, that's perfect. This bounded context is able to kind of give us that separation, even though the underlying data store is still one big thing. Now, that does mean that we need to start treating it like different databases. We can't, cheat and reach over into the other guy's tables, but it does allow us to start to think of a monolithic database as if it was lots of little databases. Bounded context is really cool. Let's take an example. So we have a shopping cart. If we're looking at a shopping cart, what is the data that this shopping cart needs? Well, we need a product catalog, and we probably need a read-only view into the product catalog. We'll need all of the product images, all of the descriptions, the really elegant, detailed descriptions of this product. We'll need a way to create orders. So, order insert, order detail insert. But that's it. We don't need to do a whole lot more with customers, with order inventory, with, all kinds of other pieces of our system. We just need to be able to create orders, and we need to be able to read products. By comparison, let's draw a different bounded context as we start to talk about shipping and delivery. In the fulfillment center, we need access to update orders to be able to set the status as delivered, but we don't need to be able to create orders, and we don't need to know anything about the product details or the product images. All we really need is the part number. Now, we might need to adjust inventory as we do this. So, pull one out of the warehouse, put it into this order, put it in the box, and ship it off. But for the most part, we can draw this bounded context around updating orders, and that's it. The bounded context between these two pieces overlap a smidge, but not a whole lot. The bounded context around the shopping cart is focused on the product catalog and all of the details. The bounded context around the fulfillment center is focused on updating inventory and updating order status. That's really cool. We can start to think of these as separate microservices with separately owned data stores, in spite of the fact that maybe we have one big database still. That's really cool. Now let's talk about micro databases. And I just made up this term, but I kind of like this term to kind of mirror the way that we do microservices. We refactor our code into microservices. Each service owns its own data in one or more data stores, and those data stores are micro databases. When we get to the point where we can automatically enroll our database in backup and restore and enroll it in authentication mechanisms, then we can get to micro databases. We probably need some automation around this. We probably need a mechanism to spin up databases really easily. Maybe we need a portal where different departments can spin up the data stores that they need. So we don't have ad hoc DBAs running around trying to install another version of SQL Server. At the point where we get to that automation enough to get to micro databases, now we have a lot more options. What's really cool is when microservices own their own data stores, and we have all these micro databases, the databases don't all need to be the same kind of database, which is actually really freeing. Now, because we can build a microservice with the data store that makes sense for that microservice, then we can start to explore other database vendors, other database types. Maybe one's better as a SQL database, maybe one's better as a NoSQL database, or as a graph database, or a key value database. When we have the automation to be able to get to microdatabases, we can pick different databases. A micro database owned by exactly one microservice, and other microservices that may need access to this data will call this microservice to get at that data. A micro database is accessed by exactly one microservice. So that's kind of our mythological definition, and we might hit a few problems as we get to micro databases. Well, for example, how do we do joins? If I want to build a report that kind of harvests all the details, does that mean that I'm going to have to call this other microservice in a loop to get each order detail? Well, kind of, and maybe not. As we build up these microservices, we may choose to publish events on an event bus like Kafka or enterprise service bus like Event Hub. And in these event buses, we can publish the events that happen within this microservice. So we have one large enterprise bus across our organization or across this project, and it's able to transmit data between services. Now it can transmit data as much as it wants, and then we can create subscribers to that data that allow it to notice changes. Maybe in that shopping cart example, we publish an event that says, I created an order. And then in the fulfillment section, we listen to that topic, and we pull down new orders that are created that need to be fulfilled. Or maybe there's a service in between, a billing service, that pulls down the order, noticing that it was created, and charges the credit card. If the credit card charge was successful, then it'll publish a new event that the fulfillment service can pick up. And if the credit card charge is not successful, maybe it forwards off a different event that customer service can pick up to go call that customer and start to complete the order. This enterprise service bus allows us to free ourselves from doing joins. We can subscribe to the data that we need from other services. And then when it comes time to join, well, we already have all the data that we need. And we may only have a subset of the data a subset of the fields in the original data store. Because as we subscribe to that, we only needed to grab the particular details that we cared about. So the fulfillment service doesn't need to keep track of all of the product name changes, and the product catalog doesn't need to keep track of all of the package was picked up notifications. But rather, each service can publish all the events that it needs to and subscribe to only that subset that it cares about. The enterprise service bus is a great way to communicate between services in less of a pull model, but in more of a push model, where we can publish any of the events that we need and pick them up with whatever other services need to consume them. Micro databases doing joins, that's really cool. Here's another example of a place where micro databases might feel a little weird. So who owns the customer record? Well, we can think of this in lots of different strategies. Well, the shopping cart may need the customer record because we're creating an order for a customer. So maybe the shopping cart is the service that is the bounded context for customers. Well, kind of. Billing probably has sensitive data like credit card information in the customer. So maybe billing needs to own the customer record. Or human resources. Human resources is full of secrets, and they really want to keep their secrets secret. So maybe human resources needs to own the customer record because some customers might also be employees. Or maybe sales. Customers probably came in through sales as leads. Pardon me. And a lead or a prospect is kind of a very different animal from a customer. A lead, I may just have a name and a phone number because that's what they wrote on the back of my card, or that's what they typed into my phone. But a customer that places an order needs to have a full name, a full address, all the way down to zip code, maybe phone number. We need to have all of the particulars for our customer. So if sales was to own the customer record, then we may end up with lots of customer records that are invalid for purchasing. So who owns the customer record? Let's create a new microservice and call this the customer microservice, or maybe the account microservice. Now, in this data store for this customer service, we have two columns. We have the primary key and we have the account number. In this customer microservice, its sole task is to accept new customer records and ensure that the account numbers are unique. That's all. It returns the primary key. In all of these other systems, they may have a customer profile table that adds additional details to this. In the shopping cart, maybe they don't have anything, or maybe the profile detail identifies previous purchase history. In the billing bounded context, then we might have the credit card information. And so that has a foreign key off to the customer microservice. Human resources can keep all of their secrets safe, knowing that they just have a foreign key off to that customer microservice. And sales, as they create a new customer, maybe as they promote a lead into a customer, they just call the customer microservice and say, here's my new account number, I'd like a new primary key. That customer microservice then can publish the events of, hey, I just changed my account number, or I created a new customer. And so then all of the other systems that need to know about new customers and initialize their profiles can either do so then or do so on first purchase or whenever they need to. The customer microservice is that bounded context against only the bare minimum of customer details, and all the rest of the customer details exist in customer profiles in those other bounded contexts. You know that customer record that gets really, really wide because everybody wants another field in it? We just solved that problem too, because all of the details that we be customer specific are now in each bounded context customer profile table. So yeah, we may end up with a billing customer profile and a shopping customer profile and an HR customer profile, and that's perfect. Each of those are bounded contexts. As we get to the point where we can move from bounded contexts into micro databases, each of those are separate databases. In the shortest term, maybe they're just separate namespaces inside SQL Server, and that's totally fine too. So that's micro databases. Any questions on micro databases or on automation of how to get from here to there?
Feel free to unmute or raise your hand or post to the chat if you've got a question for Rob.
Hi, Rob. Thank you for the opportunity to ask a question. Have you ever considered that the main problem of micro databases and microservices is actually the transactions between microservices? Let's say you have posted something on service bus and a couple of services executed very well and the other one failed, and you need to have quite complicated mechanism how to roll back all actions that's been done in other microservices.
Good call. Transactions across microservices. I like it.
Yeah.
I'll propose an analogy here. When I go into Starbucks and I say I would like my big extra mocha double pump, I don't drink coffee, so I have no idea if I'm doing this right. They don't hand me the cup and then pour in the water and then fill it up with stuff and then put the foam on the top and finally give me a lid. Rather, they give me a ticket. Well, they take my name. Similar if I'm going to go book a flight or purchase something on Amazon. My order and I push go, and it goes through a bunch of processes. And all of those processes kind of happen behind the scenes. The cool part there is if the cup overflows, as a consumer, I really don't need to know. But behind the scenes, they have failure processes to look at that. As we publish to the enterprise service bus, we can publish our success and our failures, And the shipping service needs to find a success in all of these other services before it starts to pack the box. But the billing microservice probably doesn't have as many dependencies. When we're ready to roll back, when the billing service says, no, I can't charge the credit card, we may not unrun the order. We may choose to just mark that one as failed. Can we craft mechanisms that are distributed enough where we can get to eventually consistent systems where individual failures or successes aren't dependent on other things? Now, that's a tall order. The answer may be no, in which case we may do REST calls out to the other services. And once those REST calls succeed, then we're able to publish the enterprise service bus that we've accomplished this task. If we can't get into that disconnected like scenario, then yeah, we need to get a more tight coupling between these microservices. And at that point, the additional weight of the HTTP call might become a deal breaker, in which case maybe super small microservices aren't the answer, and we need to, move more towards macro services. Maybe our microservices were too small. That's a great question. I love that.
There's another question in the chat from Andres, sort of about reporting and how do we do a report if you've got different databases with the data in them?
Good question. So how do we do reports? That's kind of the classic join example where I need to be able to pull data across many services. And that's where event sourcing, that publishing to the enterprise service bus, can be really helpful. Hopefully, the report microservice can listen to the enterprise service bus and gather all the information as it happens. So when the time comes to do the report, first off, it probably doesn't need to do a whole lot of calculations to accomplish its task. And also, it probably doesn't now need to reach out into any other data stores either. It already has all the information that it needs to be able to accomplish that task. Now, that is kind of a lofty goal, and we need to architect carefully for that. In some cases, that's where I go, micro databases was cool, but I just need to get my report done. And so I'll kind of break the bounded context, or I'll go reach around into the other guy's database in a read-only fashion. But I understand in doing so, I'm breaking that rule that each microservice owns its own data, which means my report microservice is likely really fragile. So the more that you can listen to the enterprise service bus and consume that data, the more robust that report can be. Yes, you need to work out your domain boundary or build a data warehouse. Great assertion there. When we get our bounded context right, then we don't have a whole lot of overlap between things, and we can really make those reports sing. That's cool. So let's assume that we've gotten to micro databases, we've gotten the automation in place, each microservice owns its own data. What's really cool here is that they don't all have to be the same type. We can start to experiment with different types of databases, different vendors, as long as we can subscribe them into this authentication mechanism and this backup and restore mechanism, ideally with automation, then we can start to experiment with lots of different types of data stores. I like this quote. It was said by me right now. I love puns. Okay, so micro databases. Because they can be different types of databases, let's start to explore different types of database and see when each one makes sense. And this is where we can dig off into lots of really cool experiments. For the most part, when we're coming at this, we're like, well, SQL Server all the way. A relational database is really cool, but there are other database types. And as we get to more micro databases where we're publishing events across event sourcing, then we can look at these. NoSQL, or a document data store, a graph database, key value, time series, search, object, event sourcing, column store, and one you may not have heard of, NewSQL. Let's dig into each of these, and I'm going to work really diligently not to pitch a particular database, but let's look at the characteristics of each type of database, the pros and cons of this storage mechanism. and some best use cases. I'll also give you some examples so that as you're Googling for databases of this type, you can kind of get past the blank wall. So first up, SQL. Now, the cool part about SQL is we can think of this kind of like an Excel spreadsheet or like a Google Doc. We've got tables that are rows and columns, and we can reason about this pretty easily, which is cool. In time, we might want to split this into multiple Excel spreadsheets. So maybe we have a customer spreadsheet, a customer table, and an order table, because a customer may have more than one order, and we can't exactly, stuff that into place. So the cool part about a relational database is each column stores the same kind of data in that. When we have an address field, it will only store an address. And when we have a phone number, it will only store a phone number. That's all of the data in that particular column. And then we have one row per thing that includes all of the columns. So we'll have the name and the address and the city, state, zip, and the province and the phone number and contact details. All of the different particulars in that table, each row and each column, we can think of that as the spreadsheet. What's cool about a relational database is we have this really cool query syntax that is more or less the same across all relational databases. It's been tuned for decades to be really fast and compatible. Yeah, there's differences the closer you get to like Oracle and MySQL and Postgres and SQL Server, but the majority of the pieces are the same, and it's really been tuned. So storage and query have been tuned separately and to work together really well. One of the particulars about SQL that is really cool is ACID compliance. Let's double click into ACID compliance and take a look at that. As you grab these slides from robrich.org, you can click here to learn more about this. And I really like this article, acid versus base. I really like that analogy. That's fun. So with ACID, we're assured that the entire transaction will either succeed or fail at once. We won't get part of the transaction through and part not through. This is kind of that example of, how do I get multiple microservices to all complete successfully or fail together? ACID compliance is exactly that scenario. When I create a transaction within an ACID compliance database, I know that all the things will succeed or they'll all fail together. And SQL databases are really, really good at ACID compliance. By comparison, we have eventual consistency. The example of the Starbucks coffee cup is a great example of eventual consistency. Airline tickets is another good one. Buying from Amazon. You may get to the purchase screen and you click buy and they don't tell you that the credit card failed. They'll send you an email in a few minutes if the credit card failed because it's that disconnected. Another great example is my credit card statement. At the end of the month, I know I'll have a statement that tells me everything that I bought that month. But as I quickly swipe my card, if I go check my statement balance right away, it probably won't be there yet. That's a write and then a read where the read got stale data because this database is, eventually consistent. Eventually, the vendor will send my purchase to my credit card company. Eventually, my credit card company will show it to me on my statement, and eventually I'll pay for it. But right at the point of purchase, I don't have an entirely consistent system yet. So eventually consistent versus ACID compliance. Relational databases are really good at ACID compliance, which is really cool. So as we look at relational databases are really good at having a strong schema that keeps all the data separate. We can do joins between table. We have this engine that has been tuned for decades to be really, really compliant and fast. And we have this familiar SQL syntax. On the downside, it was an engine built to be optimized for storage. When we start talking about third normal form or fourth normal form, it's about reducing data duplication so it can be stored really compactly. Now that we have an era where we have terabyte drives that we can put up our nose, Richard Campbell likes to talk about how much storage can I fit up my nose? I think it's a really nice metric there. When we have gigabytes and terabytes we can put up our nose, maybe data duplication is not our biggest enemy anymore. SQL databases were also designed when single processors were really the thing. And so we don't have a good sense for how do we scale these up. The way I scale up a SQL Server or another relational database is I just buy a bigger machine. Well, there comes a time when there is no bigger machine, or the bigger machine is so cost prohibitive that I really can't. And so SQL databases typically can't scale horizontally. Yeah, there's replication, there's transaction log shipping, there's mechanisms to try and get content from one machine to the other, but they're not horizontally scaled. They're not working in concert. Rather, the other machine is just kind of doing all the work too. And so we may write to one, have it publish to the other, and read from the other. So we're starting to pretend it's a cluster, but it really isn't a cluster of machines. It's really a bunch of databases strung together. SQL databases tend to have this concept of horizontal scaling as a bolt-on at best. So because we have a strong schema, we do need to migrate that schema. So we need to tell our database when our application business logic changes to add a column or remove a column. So that's relational databases. Here's some examples of relational databases. For the most part, relational databases are great when you need to do, well, the basic things. If you're in a monolithic database world, it's probably a relational database, which is pretty cool. You chose correctly 10 years ago. That's awesome. Next up, document databases. Well, document databases, we think of them as NoSQL databases, but kind of anything that isn't a relational database is, well, NoSQL. In a document database, generally we store data as documents, as JSON blobs. Now, we might store them as BSON, that's what Mongo likes to call it, where it's binary encoded JSON, but it's still a JSON document. The cool thing about JSON documents is that, well, we can nest data. So we can have embedded collections, we can have arrays, we can have nested objects. And that can be really good in describing exactly what we want this document to be. Well, each document ends up in a collection, and these collections don't necessarily need to be the same between documents. We can have different documents with more or less fields. We can have more or less items in arrays nested in documents. On the upside, that schema-less type of mechanism allows us to code quickly. On the downside, well, our application has a schema, and so the fact that our data store doesn't might kind of get in our way sometimes. NoSQL databases are generally eventually consistent, and they're really optimized for reads. So we'll build this object, this document, in exactly the way that we need to read it. So, for example, so document databases are great when we need to pull out all of the data and display it really quickly. Because it's optimized for reads, we're generally really fast. And then we understand that writes might be slower. Maybe we need to update a couple of documents to get that data change propagated. But inside that document, we can do all kinds of really interesting things. Nest fields, nest inner documents. And so we really don't have a schema that we need to migrate. That's really cool. On the downside, our application probably has a schema. And so we need to do things like, well, what happens if we get a document and it doesn't have a field? How do we query inside of the lack of fields? Show me all the documents that don't have this field. That can be kind of one of the downsides of a document database. There are mechanisms to try and migrate these schemas or try to enforce a schema, but document databases generally don't have this. They are clustered, and so we probably have a mechanism to scale horizontally. We probably have a mechanism where lots of machines can participate together, and that's really, really helpful for document databases. So document databases are great for maybe a product catalog or a news site or a CMS, where I need to be able to grab all of the pieces of this news article. I want the article title, and I want the article copy content, and I want the author's name and the author's picture, maybe the first few comments, maybe the published date and the author join date. I need all of those things in one place so I can read it by the ID of that document and publish it really quickly onto my website. That's a great use case for a document data store because all of that data is optimized for that read. We can pull it in one place and just dump it in a place. Here's some examples of document data stores. And I see a question here. Missing one point of cons, speed of aggregation. Unless you do crazy load of materialized view. Good point. Was this about document databases or was this about SQL databases, Jack Nee?
I'm assuming that was for SQL. Yeah, relational.
Yes. Speed of aggregation. Unless you do a crazy amount of materialized views, then you need to, you need to play with how does your schema look. Good call. Any questions thus far on SQL and document data stores?
Rob, have you done much, I guess, where you've used both and actually ended up duplicating data between the two different types of databases just for different purposes, so using one for reporting and another for other kinds of operations?
I have. Reports really like that relational type of system where they can dig into and group and aggregate. And transactions may be great for, I just want to dump this object into place. Or maybe I just want to dump this object into place and have a later service downstream normalize it into all the tables. So depending on the needs, the speed of the system, I have used both in context. Or we'll get to hybrid databases when we get there. Maybe we can have a JSON column inside of a relational database acting like a NoSQL database for those things that we need that are, pieces of NoSQL-like behavior. Usually, I only need one or the other, but I have seen cases where I need both. So NoSQL database, document databases, I keep calling them NoSQL. Let's dig into the next one, graph databases. What's cool about graph databases is graph databases focus on relationships between things. So we have nodes, but we also have relations. Now I can store data either on the node or on the relation, and that becomes really helpful. Relations can be directional or bidirectional, and we have this really elegant mechanism to traverse those relations. We can think of these as like friends and friends of friends. That's kind of a good example for graph databases. So we have kind of a SQL-like experience, but we have this really elegant query mechanism that allows us to traverse those relations in really elegant ways. So how is this different from a SQL table with two foreign keys? Maybe we want that relation table that just has foreign keys back to both regular tables, and we may want to put some additional columns on it. Well, yeah, it's kind of similar, but what comes really powerfully in graph databases is that query mechanism of being able to traverse those relations in a really elegant way. Yeah, I can interjoin myself 3 times to try and get friends and friends of friends, but it gets kind of painful. This is really where graph databases excel. So on the upside, with a graph database, I get that friends and friends of friends experience. I can store data on nodes and on relationships. On the downside, I've kind of traded a lot of other things for this. So joins in graph databases get kind of expensive because, well, it's not really built for joins. It's built for traversing relationships. So graph databases. Here's an example of a graph database as you're Googling for similar ones. It's great for messaging apps, for social networks, maybe for recommendation engines where you want to find related products or related friends or be able to traverse those relationships. That's where graph databases really come in handy. Maybe on the relation, you store the date that that connection was created, but maybe all of the social connections, all of the messages between these, maybe that's not stored in this relationship. Maybe that is better stored in a SQL database where I can normalize that data. Next up, key value databases. When we're looking at a key value database, we have a key that is, whatever we need it to be, and we have a value that is a big blob of stuff. We can think of this as a SQL table with 2 columns. Now, the cool thing is that data doesn't need to be the same between each row. So maybe one of them is the configuration details that we need to connect to the database, and one is the shopping cart details of the user with this username, and one is, we can think of this as great for configuration or cache data to be able to get at stuff. Pardon me. It's really good for get by ID mechanisms. And then once we get that big binary blob, then we can deserialize it. Maybe it's JSON, or maybe it's XML, or maybe it's just text. And we can start to look at it and deal with it in the way that makes sense. So as we're caching data, maybe different pieces are actually different types of things, and we might need a different deserialization mechanism to get at each one. Maybe some are XML and some of them are JSON. With a key value store, we're focusing on get by ID. And with a get by ID, we can get data really, really quickly, and we can save data really quickly. Great for caching mechanisms. On the downside, there's no such thing really as a where inside the other thing. I can't really filter on any other kind of content because, well, it's just an opaque blob to the key value database. The way to filter by other things, or the way to get all, is really to get every key and deserialize it in the way that makes sense, and then start to look through it. So if I need additional metadata or additional where filters, then a key value database may not be the best choice. Or maybe I have that metadata database in a relational store, and the key value database is just about getting at that binary blob. Once I've got that primary key, I can do a get by ID inside the key value database, and I've got that data really quickly. Here's some examples of key value databases. Redis is definitely famous for this. It's great for cache and configuration, user session data, the things where I know I'm going to get and put by ID, where I don't really need that to get by any other columns, where I'm just storing this data exactly that by ID. Key value databases. Next up, time series databases. Time series databases are great when I have time-focused data. It's really good for fast ingest of real-time events. It's really good for querying based on a time window. Now, this is really cool. Usually when I'm querying, I'm going to query by a particular set of conditions, and I'll end up with rows and columns, and the cells in each place is a single value. In a time series database, I might have a time bucket that is 5 minutes or a day or a month. And inside that cell, I don't have one value, I might have many values. The cool thing about having many values is now I can do really interesting things like, well, let's sum them, or let's aggregate them, or let's find the min and max, or the count of the items inside that cell. Now, cell isn't a great thing. Bucket is probably a better word there. All of the different pieces of data inside a time series database can be windowed in that really elegant mechanism to grab insights into those. Well, what about cells that have no data, or cells that have extreme data? That's an interesting thing that a time series database can help harvest. Or maybe we use those buckets, those time windows, to be able to normalize out spikes so that we don't have lots of bumpiness in our data. On the upside, those windowing functions allow us to do a whole lot of really insightful things on our data when it is time focused. On the downside, we've given up a lot of other things to be able to do this time type mechanism. So here's some examples of some time series databases. Time series databases are great when I have lots of data coming in that is very time focused, maybe monitoring or real-time events for mobile devices or sensors, stock trades, click streams, things where I have lots of data flowing really quickly, and I need to be able to harvest mins and maxes, averages and conditions inside that time bucket. If you've ever seen a popsicle graph or mechanism stock diagrams where they have today's high and low and averages, that was a time series database so that it could find the details inside that cell the high and the low within that bucket. Time series databases, text search databases. Text search databases are great for being able to find documents that have matching words, or where in the document is this matching word. Now, often when we start to talk about search like this, we start to think of, Google, where I can give it a natural language query. That is definitely a use case here, but the natural language processing to be able to infer the intent of that query is a different system. Natural language processing is amazing. Once we find the intent, then we'll go look inside of a text search database for the documents that have those words, or for where in those documents are those words. Those are basically the two queries that we ask it. We have an inverted index where we take all of the words in each document and then we sort by those words. We can think of this kind of like the index in the back of a book. We can go to that section and find all of the references to a particular name or a place, and that will get us back to all the documents that have that particular name or place. On the upside, with text search databases, it's really good at being able to find that the match of documents or the places within a document that have those keywords. On the downside, it's really geared for that function and not a whole lot of other things. It only works with text. Another thing that's interesting here is stop words. When we stop words in English, we have the, a, an. For street names, we might have av, street, rud. These are things that don't really add contextual value. And if we were to grab all the A's in this document, that would be a really big collection of documents that probably has little value to us. So with stop words, we're probably going to ignore all of those words in our index, which is cool, but stop words are also very language and culture specific. So if I'm working in Spanish or in French or in German, I'm going to have a different set of stop words. Also, depending on the domain we're working in, maybe the stop words are not appropriate. In our example, we said, well, road and av and street probably are stop words. They don't have a whole lot of significance when we're looking at addresses. But what about the road in Seattle called Avenue A? Well, we decided that A is a stop word, and we decided that av is a stop word. So this address is unsearchable. Stop words are very, very language, culture, and domain specific, and we can really easily get bitten by them. So text search databases. Here's some examples of text search databases. The interesting thing is that both of these examples do it very differently. One puts the schema in on ingest, and one puts the schema in on query, so that I can, for example, say, I believe the data has this structure, query it and see. And then if I want to query it differently, it can impose a different structure on it, which is really interesting. Text search databases are really geared towards finding keywords in documents or finding which documents match. Now, the interesting thing is that, well, maybe I want to search by other things like topic or publication date. And a text search database really isn't good for that metadata. So maybe I have a companion database that has all the metadata associated with the documents, and I can pre-filter, or maybe I join the results of the text search with the results of the metadata search to be able to find those documents that have this keyword and that also are published in this date range or on this topic. So text search databases on its own will be okay, but combining those with maybe a relational database can be really, really powerful. Next up, object stores or blob stores. We can think of this roughly like a file system, and to some degree, we can misuse a file system as an object store as well. S3 is kind of the canonical example here where we have a key that may have slashes in it, and we'll pretend those slashes are folders, but there really isn't a folder behind this. And given that key, then we can have a big binary blob behind it. Now that big binary blob is, well, just a big binary blob. It's great for videos or database backups or log files, very, very big things that I don't want to index in another way. On the downside, It's great for a query by ID, but it is not great for searching on any other kind of criteria. When was the last time this file got modified? Well, basically, I would need to untar each backup file in turn going, you got one? You got one? And so this kind of metadata around the documents probably needs to get stored in a different data store. But once I've identified which document I want to get at, then I do a query by ID into my object store, and I can go read the contents of that backup. I'll deserialize it in the way that makes sense, and then I'll use that data. Blob versus block. Read fast versus write fast. Good call. Yeah, I've kind of glossed over blob and block differences. Thanks for calling me out there. Is blob significantly different from a key value database? In principle, it really isn't. In usage, usually it is. A blob store is focused on storing really big things, where a key value store is focused on storing and retrieving things really quickly. And so that's kind of the main difference between them. When we think of like Redis versus Amazon S3, then we kind of see how those would be used differently. With S3, I probably want to store, images or files. With Redis, I probably don't want to store a file inside Redis. I probably only want to store, the connection string or their shopping cart in case they log out and need to log back in and grab it again. That was a great question, Ryan. Thanks. So here's some examples of object stores. Amazon S3 is kind of the canonical example. And so there's things like min.io that will create a similar type of S3 experience, but not on top of S3. And there's other mechanisms that will kind of shim that S3 API into other places. It's really great for storing big things, but it's not great for querying on other metrics. So we might have a companion data store that stores that metadata. Next up, event sourcing. Event sourcing is really cool. It's that pub/sub mechanism, that way of publishing content from one system and consuming it in another system. Here in this diagram, we have a producer that will write new records onto the end here. So it's in the process of writing number 9. Then we can have various clients that will keep track of what's their current number, or maybe the system keeps track. So this consumer is reading record 8. It's almost caught up. And this consumer is reading record 6. It's a little bit behind. In time, all of them might have caught up enough that we might want to trim old records off the end. So maybe 2 is no longer valuable anymore, and let's start to delete it. We've already deleted number 1. We have this mechanism where we have this process of publishing all the events and asynchronously consuming them from somewhere else. Unlike an HTTP call or a REST call that must receive the answer right away, we can publish this into the event store and consume it whenever we're ready. So if a microservice goes down, the other microservices around it aren't stopped up trying to retry the calls to be able to tell that other microservice about the data. They publish their data to the event store and they move on, which is amazing. Now we can compensate for failure. Maybe consumer A had gone down for a few days and needs to catch up. It knows where it was, so as it comes back online, it just starts reading away and consuming all the data. Or maybe we changed our business rule and we now need to replay from the beginning to recalculate where we are using a different set of assumptions or capturing different quantities of data. Event sourcing is a really elegant way to publish and subscribe in an asynchronous, disconnected way. So event sourcing, it's really great at asynchrony around pub/sub. It's a way to handle disconnected or hardware failure scenarios where we can catch up later in an asynchronous way. That's really cool. On the downside, it is eventually consistent by nature. So if I need an ACID compliant transaction, then event sourcing is often in the way. I need to compute everything to get the current version. There is no concept of the current version in event sourcing. Rather, the current version is the sum of calculating everything. So in time, we may want to grab snapshots to say, here's a good starting point, and from here on, now you can recalculate it. Or maybe we keep the current version in another data store that allows us to catch up faster. Sometimes this data gets really large and we may need to drop old records. At that point, well, what's the beginning? As we expire old records, we probably need to get really good at capturing current snapshots so that we can get caught up from here on. So event sourcing, here's some examples. Kafka is kind of the canonical example, but there's a lot of good data stores here that allow enterprise event sourcing. It's a great way to transmit data in disconnected scenarios, and it's a great way to compensate for hardware failure. Column stores. Oh, before we go there, MinIO is different. It's SDS. Yeah, the API is identical, but the lower storage is completely different. I completely agree. It's kind of Squint and Grin and S3 compatible, but it's not exactly the same. If you're assuming that it is identical, then from a high compatible enough for the majority of uses. Good call. Ooh, you've been using it for a while and wrote extensions on it. Very nice. We'll have to get together after this talk and share MinIO stories. Or perhaps a future Adelaide.NET group talk could be on MinIO. It's a really, really cool tool. Rook is better. Yes, enter the storage wars. Next up, column stores. Column stores are really interesting. They're an adaptation of a relational database, but they kind of turn the concept of relation on its head. Data is stored in columns and segments instead of rows. Here on the left, we have a relational table where all the data is stored in rows. And so if I have a null field right here and I fill it with data, I may need to move this off of this page into a different page to be able to get all that data together. Or perhaps I have to have a split page to get my rows to work together. But I know that this row is all of the detail associated with this table. By comparison, here's columns. And we have columns. We can kind of think of these as the indexes, kind of, not really. Column stores are really good because they have that mechanism of all of the data associated with this column. Think of this states or provinces or countries. Well, there's only 200 and some odd countries in the world. So we know that if we're indexing our data by country, that index is going to be really small. So we can get all the way to the Australia section and we can read all of the Australia data really easily. And then once we get to the Australia section, now we can get into different data. With a column store, it's really easy to do analytics. It's really easy to do bulk reads and writes because all of the data is stored here in the column. The column then links off to various segments that may contain the additional data. By comparison, row stores are really good for transactional data where I need to do random reads and writes. I need to get to this row and I need to update all the pieces. Where column stores are good for bulk reads and writes because I can just cruise down to this particular thing and read all of the data associated with that. So column stores, it has much better compression. If you have a lot of bulk data that is similar-ish, then you'll probably have a lot better compression by putting it in a column store because, you know, all of the Australia pieces kind of fit in the same box. That's really cool. It's better for faster seeks when you have lots of big data, but on the downside, it's not great for random reads and writes. So if you're using it as a transactional store, then it may not perform very well. Some example of some column stores. Column stores work really well for OLAP, for analytics, where I need to do bulk reads and writes and then computations over the top of a lot of data. If you're doing transactional data, you may choose to put that in an OLTP database, a transactional database, and then you might do ETL to get data from one to the other, or maybe event sourcing to get it from your relational into your analytical store to do analysis. Maybe this is your data warehouse, the column store. So next up, NewSQL databases. NewSQL databases is another mechanism of kind of turning relational on its head. With a NewSQL database, we have a SQL database with ACID compliance, but it is partitioned across commodity hardware. So in this example, I have 6 machines. I have an aggregator node, another aggregator node, and I have leaf nodes that store the data in partitions on each leaf. Queries will come into the aggregator node, and they'll get distributed to all of the leaf nodes that need to participate in this transaction. The leaf nodes will collect data out of their partitions, push that back up to the aggregator node, and then the aggregator can turn that into a deterministic query and return it to the client. The cool part here is that as we need to scale up, we can just add more machines. In this case, we only use 6 machines. We could use 20 machines or 200 machines. And so we can think of NewSQL as a great way to do SQL with an SLA. We want to return consistent read speed and consistent write speed by using commodity hardware rather than one big machine. We still get ACID compliance, we still get transactional safety, but we do so with much cheaper hardware. We're distributed by default. This is really cool. With NewSQL databases, it's that great merge of the horizontal scaling of a document database together with the ACID compliance of a relational database. On the upside, it's a lot cheaper to scale a NewSQL database because I just add hardware. On the downside, when I'm doing a join, I may need to move data across the network between these machines. Maybe if I'm joining this data with this data, I need to copy some of that data across the network. Now, these machines ideally are on the same LAN. Maybe they have gigabit NICs between them. And so probably that network latency is negligible. But it is one of those things that we do need to be cognizant of because we are adding a little bit of additional network latency into this process. So here's some examples of some NewSQL databases that allow us to do some really, really amazing things with SQL. If you have a dashboard where you've gotten to the point where you have that spinning wheel too much, a NewSQL database may help you break free from MySQL or Postgres not being able to scale up. When you get to that point where you've outgrown your SQL database, a NewSQL database can be a really, really good choice. So now hybrid databases. Well, maybe I need this and that, or maybe I need mostly SQL things, but I also need a little bit of this other thing. Maybe I want SQL, but I also need a little bit of NoSQL-ness. I need to be able to nest things. So now I'll use a hybrid database that has a JSON column in it. Or maybe I need mostly SQL, but I also need time windowing functions. So a hybrid database can kind of build this up. I see a lot of databases moving in this direction. And so as I kind of identified each database in their category, it could be said that some of them don't really fit in those categories anymore because, well, they're hybrid in nature and they do this and that. If you're getting into a monolithic scenario where you need these capabilities and a little bit more, maybe a hybrid database is a good choice for getting to that additional functionality. As you get more to micro databases, maybe a hybrid database will reduce the number of vendors you're supporting, but you might want to specialize on specific databases. Or maybe you do need a hybrid database that allows you to do some things and a few other associated with specific needs inside of a microservice. So here's that money shot. Grab your cameras and take a picture of this one because this is the really cool spot where we have all of our databases summarized nicely. The name of each database, kind of a really short description of it, and when it's best useful. So digging it a little bit farther, when we look at our systems, we looked at moving from monolith to micro databases. Now we chose a monolith database because, well, it was difficult to get at lots of setups. As we can get more automation around our system, we can get from a monolith to micro databases where each microservice can own its own data store. Until we get there, we can use bounded context to kind of simulate micro databases, where those bounded contexts allow us to kind of separate the data and pretend it's micro databases. We looked at each of these data stores and kind of looked at the pros and cons associated with each one and when we might choose each one, examples of each one. You can grab these slides from robrich.org right now and dig into each of these databases and kind of Google some more to find the database that is exactly right for your problem. So what would I recommend? Well, probably a good default is a SQL database. If you have a monolithic database, it is probably a SQL-based database. At the point where you need something else, then definitely go shopping for other database types. Maybe a hybrid database gives you that SQL transactional ACID compliance comfort, but also gives you some additional features as well. Or maybe it does make sense to get into a specialized database that really optimizes for your scenario. Whenever possible, use database as a service, because at that point you could go back to sleep and your vendor is responsible for uptime and point-in-time restore and continuous backup. If you find a scenario that doesn't quite meet a SQL scenario, then other databases might be exactly the scenario that you need. But be careful as you start wandering away from SQL databases, because those things that you took for granted with the SQL database, like the really easy queryability and ACID compliance, may not be there in your other databases. Fun to dig into all kinds of databases. What are your thoughts and questions? What did I get wrong?
Again, feel free to unmute or to use the chat room. Rob, there's a couple of things that stood out to me in that talk. One was, I guess, the being able to mix the event bus with microservices. It's, I think, for some reason, some people might sort of have thought, oh, the event bus, service bus, that was a thing from a few years ago, and now we've moved to microservices, and we'll shift over. But actually combining the two is quite a valid solution.
Yeah, it's a really elegant mechanism to kind of be able to publish and subscribe through microservices so that they can be truly disconnected.
Yeah, and I guess the other thing that I appreciated is just so many different tools in the database toolbox, that it's not just the relational database and not just NoSQL as well. There's a whole lot of other kinds of databases out there that could be the right tool for the job.
Right. I'm enjoying the comments. Thanks for the talk. Very practical. So glad you enjoyed it. Can view the deck, but not view it offline. You're right. One of the benefits of having my decks as a website is that you can view it on your phone. You don't need to download PowerPoint Viewer, but yeah, you're online. I have hit up the page and then taken my machine offline, and it still works. You can navigate between slides that way, but I agree. Sorry, I can't forward you a PDF. Never occurred to me to go database shopping. SQL always appeared to do the job. We'll definitely dig into this some more. I'm glad you enjoyed it.